Well, good evening, AP Physics students. Mr. Kurse coming at you here, talking a little optics today. We're going to bend the truth a little bit today. We're going to bend some light, talk about refraction, talk about total internal reflection, talk about fiber optics, talking about lots of good stuff. So, let's start out here. Remember that speed of light, that thing that we said is a universal constant? And it's so constant throughout the universe that we even give it the symbol c. Well, as it turns out, you can change the speed of light. You just have to change the medium in which the light is propagating through. So while it's true that the speed of light in a vacuum is a universal constant, no matter what speed you're traveling according to Einstein, light does change the speed at which it travels in a different medium, okay? Now, the n value, which is just a number, is called the index of refraction of the substance. Refraction is the bending of light, okay? So light changes speeds, and it slows down. It always slows down. The vacuum speed of light is the fastest speed there is, but then light slows down when it goes through other substances. So it is 1.5 times slower in plexiglass, 2.4 times slower in a diamond. In air, it's only slightly slower. For all practical purposes, the same. So light slows down when it enters a new medium. Now, you may ask, why does it slow down? Well, as it turns out, when light slows down, its frequency still stays the same. So let's say you have a photon that has a frequency of 10 to the 14th hertz, or 10 to the 14 waves per second. Well, that frequency, or the number of waves hitting, say, a piece of glass, that can't change. So in order for the speed to change, what happens is the wavelength of the light gets shorter in the new medium. So sometimes we say that lambda goes to lambda sub n. In other words, if the index of refraction is 2, the wavelength of the light is only half as long. And since the wavelength is half as long and the frequency is the same, that means the speed of light is slower by a factor of a half. Okay, what else happens to light as it enters a new substance, say from a vacuum into a piece of glass? Well, as it turns out, the light bends. If you've ever been, looking at a swimming pool, and maybe you put like a pole or a net in a swimming pool, it looks like as the pole goes into the swimming pool, it looks like the pole bends. But as it turns out, this is just kind of an optical illusion. If light comes in, say, from the air, and the light is going into, say, water, right? Air has an index of refraction of roughly 1, water about 1.33. The light will bend towards the normal, okay? And there's a law that explains how theta 1, n1, n2, I should label these here. This is n1 going along with theta 1. This is n2 going along with theta 2. And the law that explains how this works is called Snell's law, okay? And basically what it says is n1 times theta 1, sine theta 1 is equal to n2 times sine theta 2. So light bends towards the normal when it goes to a higher index of refraction. It can bend away from the normal if it's going the other way, okay? Now, the next thing I'm going to talk about is total internal reflection. And I tried to draw this, and I didn't do a very good job, so I'm going to revert to the book, all right? So if I have a flashlight underwater and I shine it up, the light ray will get bent away from the normal. Now, some of the light will be transmitted from the water to the air, but some will be reflected also. And there's a special angle that occurs, and it's called the critical angle. So let's say I have a source of light. Well, this light is bending away from the normal. Here, this light's bending away from the normal. And here I get to a special angle where there is no light that gets transmitted through the medium. All of the light gets reflected, because what happens is this angle ends up being 90 degrees. And of course, light that's perpendicular to that normal basically isn't getting transmitted at all. So that special angle is called the critical angle. All right? And it's important because fiber optics, which is the carrying of a light signal through a cable, depends on total internal reflection. And we'll show you an example of that in class tomorrow. So that's some good information here. Let's use some of this information to solve a problem. Let's go for problem 26 here out of chapter 23. So in this problem, it says that a beam of light is incidence onto a plate glass. And it's incident at an angle of 63 degrees. At what angle will it come through the glass to the other side? So light is bending here as it enters the new medium. What is the angle at which it's going to be bent? So this is a straight algebra Snell's law equation. N1 sine theta 1 equals N2 sine theta 2. And we can do a little algebra here and solve for the new angle, which would happen to be 34 degrees there. Okay? So those are some hints on how to solve problem 26. Now, these three new equations we just talked about here, would just like to show you here where on the equation sheet they are, right? So you know the wave equation, speed of a wave, frequency times wavelength. Here's how the AP defines n, or the index of refraction. We've got our Snell's law and our critical angle. And of course, yesterday we talked about lenses and the focal length being half of the radius of curvature and magnification equations. Excuse me. So, lots of good equations on our waves and optics section there. So, nice work, physics students. We'll leave you with an interesting article from the paper the other day. Are your genes yours? The Supreme Court is weighing in on whether gene patents are valid. Can someone patent your genes? And by your genes, I don't mean, your Levi's or your Guess or your, I don't know what kind of jeans people wear these days. But can a company patent and have intellectual property rights to certain genes? So anyway, very interesting article about what the Supreme Court is weighing versus, individual rights. A company spends lots of money doing a lot of medical research. Will they get benefits by having a patent to the genes they discover? Lots of good stuff going on. All right, nice work, AP Physics students. We will see you tomorrow.